Greetings everybody and welcome back to some more complex analysis. Today we're going to be evaluating this improper integral from minus infinity to infinity of 1 minus cosine of x over x squared. So this is going to be kind of like a freestyle video. I don't even have notes or a solution prepared with me. I have a rough idea of what the solution should look like. But yeah, if you see this video uploaded, then I guess I did alright on this integral without any notes. So let's take a look at this integral. First thing I see is what we have this integrand, and usually what we want to do is we want to define for ourselves a new complex function f of z to be equal to the integrand, but we replace the x's with z's. Now in this case we have a cosine, so usually what we do is we rewrite cosine, or if we even see sines, as just e to the iz, because what we can do later on at the very end is we can take the real part of this function, and that actually should evaluate to 1 minus cosine of x over x squared. So we'll take a look at this function f of z, and right away we can notice a couple of things. We can take note of the poles of this function. I'll put it down here perhaps, so poles. And we have a pole at z is equal to 0. And on the numerator, well, nothing really happens there because the exponential function is entire, so we only get a pole at z equals 0 because of this division by z squared. I don't think we'll be using the residue theorem for this video, but we do have a pole at z equals 0. So with this information we can construct our contour. Now if we draw up the imaginary plane over here, or the complex plane rather, we have a pole at z equals 0. So we have a pole right over here. And now we want to integrate from minus infinity to infinity. So let's start at some big radius minus r over here, all the way up to r. And so we want to integrate from minus r to r, and then later take the limit as our r approaches infinity. So let's try to do that. We're going to go along here, and then we run into a bit of a problem because we have to pass through this pole. Now what we do is we can take a detour, like so, around the pole, and then we can keep going. And this detour, this little semicircle, will have a radius of epsilon. So let's call this minus epsilon to epsilon, and then we go in this direction. Okay, so we have this part. This is what we want to integrate across. And now we want to enclose this contour. We want to complete the loop. So let's start over here and then go up all the way around and back down. Well, that's an alright semicircle, I guess. Not the best one, but yeah, that should be okay. Maybe this side is a bit too big, so I'll reduce the size down there. Right, it should look decent now. And this is still our imaginary, our complex plane. Now notice that there's only a pole at z equals 0, and there's no other poles anywhere else. So what does that mean over here? This contour, let's call it c, and let's call these parts, this little part in here gamma, for example. That means that the contour integral over c of f of z dz, this is equal to 0, okay? But notice we can decompose our contour integral into multiple parts. We have the integral from minus r to minus epsilon, first of all, and then plus the integral along little gamma, and then plus the integral from epsilon to r, and then we have plus the integral along this big arc at the top, which I'll call big gamma, like so. So you have the integral along gamma as well. Now what we want to do is we want to evaluate each of these integrals over here one by one, and then we should be able to figure out what our initial integral will be from these two integrals. So I'm going to guess that this integral will contribute nothing, but this integral, it's going to contribute something because we're integrating around the singularity. Usually what happens is that when we integrate around the branch point, so for example, if we have a natural log in there or something like that, then the integral, oh, my pen just dropped, the integral around this circle would vanish, but if we integrate around a pole, then it should be some value. Okay, so let's go ahead and compute each of these integrals. Maybe we'll start off with the easy one over here, the integral from minus r to minus epsilon of f of z. Now instead of z, I'm going to say x because we're integrating on the real axis. Now we want to take the limit as our epsilon approaches 0 and our r approaches infinity. So maybe I'll put all the results on this bottom line. So this bottom line is going to represent all the results when our epsilon approaches 0 and our r approaches infinity. Notice the value of the contour will never change because it never crosses any poles. Okay, so we have this expression, but what exactly is this? This is equal to the integral from minus infinity, or in the limit rather. So let's take the limit as our epsilon approaches 0 and r approaches infinity. This is going to give us the integral from minus infinity to 0 of f of x dx. But that's exactly, well, that's not exactly what we have there. Let's actually write it out in full, just to be safe. This is going to be exactly 1 minus e to the ix divided by x squared dx. Maybe we'll leave it like that. And yes, we have this, and we also have the integral over here from epsilon to r of f of x dx. Now again, in the limits, as our epsilon approaches 0 and our r approaches infinity, this is going to give us the integral from 0 to infinity of 1 minus e to the ix over x squared dx. And now let's add both of these integrals together. So if we add both of these together, so the sum, that's going to give us overall, since the integrand's the same, we're just adding these intervals basically, we're going to get the integral from minus infinity to infinity of 1 minus e to the ix divided by x squared dx. Okay, so this, whatever this evaluates to, this is going to be the value of these two integrals. So what I'll do actually is I'll replace this with epsilon to r, and then I'll turn this integral into the integral over gamma. So these two integrals, they contribute to give us the integral from minus infinity to infinity of 1 minus e to the ix divided by x squared dx. Alright, so we've dealt with these two integrals. We have two more to go. Let's take a look at the integral over big gamma over here, because that's probably going to give us nothing. So let's do that. Let's take a look at the integral over big gamma of f of z dz. Notice I'm using z here because now we're back in the complex plane. Alright, so the way we do this is we want to estimate it, because this is eventually going to go to 0, so we want to show that there's an upper bound, and that upper bound goes to 0 in the limit. So what do we do now? We have to parameterize this integral. How do we do that? Well, we notice that for every point z on our gamma, for every complex number on gamma, we can write it in the following form. It's equal to r e to the I theta, where theta is on the interval. Well, we're going to go from 0 all the way up to pi radians. So this is our interval for theta, and now we can differentiate both sides. dz is equal to I times r e to the I theta d theta. So just using some chain rule there. So we can plug this parameterization into our integral. This is going to give us the absolute value of the integral. Now instead of gamma, we're going over the interval for our parameter, which is 0 to pi of f of z. But now f is exactly this guy over here. So we have 1 minus e to the I, and z becomes r times e to the I theta, and this is all divided through by z squared. But what exactly is z squared? Actually, what we can do, we can keep the z squared down here for now, even though we're not supposed to do that. We're supposed to change everything to theta because we're integrating with respect to theta, but we can leave that for now. And by the way, dz actually turns into I r e to the I theta d theta. But I'm going to do something that's you probably won't like. Notice that r e to the I theta, that's once again our z. So we can actually write this as I times z d theta, which is something that's a bit uncomfortable to do because we're integrating with respect to theta, but we still have z's in here. But remember, z is just r e to the I theta. And so now notice that we can cancel here and here. This z is gone. And now we have an integral, and we integrate with respect to theta, which is a real parameter. So now we can use the integral inequality to say that this is less than or equal to the integral of the inequality. So we bring these, the absolute values, we bring the absolute value into the integral. So now we have the integral from 0 to pi, absolute value of 1 minus e to the I r e to the I theta. And now this is divided through by z. And notice, this I we can ignore because the absolute value of I, that's just 1. So this is what we have. We integrate with respect to theta. Okay, and now we can split the absolute value between the numerator and the denominator. And notice on the denominator, what we end up getting is that this is the integral from 0 to pi of the absolute value of 1 minus e to the I r e to the I theta. And this is divided through by the absolute value of z. But notice, since z is always along this curve, gamma, and gamma is a semicircle with a radius r, the absolute value of z, that just becomes r. And we integrate with respect to theta. Okay, so now what can we do? We can bring this I out to the front because it's just a constant. So this is going to give us 1 over r, integral from 0 to pi. And we have the absolute value of this thing over here, 1 minus this exponential. Now what we're going to do is we're going to apply, let's see, the reverse, not the reverse, the triangle inequality. So the reverse triangle inequality is only when you have the absolute values on the denominator, but if you have it on the numerator, then you can just use the normal triangle inequality to find an upper bound. So what exactly is the triangle inequality? I'll put it over here maybe. So if you have the absolute value of a plus b, this is less than or equal to the absolute value of a plus the absolute value of b. And so you have something similar in this form. So a would just be this 1, and b would just be minus this exponential. So what we can do, we can apply this directly. We can say this is less than or equal to. So absolute value of a plus b is what we currently have. This is going to be less than or equal to the absolute value of a, well, that's 1. And then plus the absolute value of b. But b is just this negative exponential. But absolute value of that is this, well, absolute value of e, I r e to the I theta. And then we integrate with respect to theta. Alright, so now what can we do? Notice that this guy over here, in particular this e to the I theta, we can expand it out using Eulers Formula. So this is going to give us 1 over r, integral from 0 to pi of 1 plus absolute value of e to the I r. As now first part of Euler's formula is cosine of theta, and then we also have a plus I sine theta. But notice that I sine theta, if we multiply by this I, we're actually going to get negative sine of theta. So this is minus, we still have this r, and then we just have sine of theta like so. Right, this is still integrated with respect to theta. And now the nice thing over here is that we can split up this exponential. So box this over here. This is now going to give us 1 over r, integral from 0 to pi of 1 plus e, absolute value still, we have e to the I r cosine of theta, ends of absolute value, and then another absolute value of e to the minus r sine theta. So just using some exponential properties to split that exponential function up into theta. And notice one cool thing over here, theta is a real parameter. So cosine of theta is real, r is also real, it's some real radius. So r times cosine of theta, this thing is real. So if you have the absolute value of e to the I times some real number, then it's actually going to be 1, because it's going to give you some number on the unit circle. So this is going to be 1, leaving us with just this exponential. But notice its argument is real, so it's actually going to be always positive. An exponential function is always positive. So what does this become? This becomes 1 over r, and then we integrate from 0 to pi of e to the minus r sine of theta d theta. Okay, this looks pretty familiar. I think we've dealt with this before in a couple of videos. We need to find a new upper bound for this, because as it is right now, we can't really integrate it. That would be pretty difficult to do. I don't think there's an antiderivative for that function. So what we're going to do now, so far what do we have? We have that the absolute value of this integral over gamma, well, let's trace the inequalities. It's less than or equal to, and this is less than or equal to this thing over here. So far, we have that this integral over gamma let's erase all this previous working out. We have that it's less than or equal to the 1 over r times the integral from 0 to pi of e to the minus r sine of theta d theta. And yeah, you might say in the limit as r approaches infinity, this is going to be 0, but we have to make sure that this function doesn't blow up, and that might cause some issues. So you have to find a new upper bound for this thing. Maybe it will make it slightly easier to evaluate. I believe the way we did that, I haven't done this in a while, but for sine of theta, well, first of all, we take a look at our exponential function. This is a decaying exponential function. So if you take a look at the graph of that, if you pick 2 points, A and B over here, what you'll notice that for a decaying exponential function, if A is less than or equal to B, then in fact we'll do it the other way around. I think it's easier that way. If B is greater than or equal to A, then e to the minus B is less than or equal to e to the minus a. Why is this helpful? Well, if you look at this expression over here, we want to find an upper bound for this integrand, which means currently this is what we have. We want to find some kind of e to the minus a because this will give us an upper bound. Now notice, we can say, well, r sine of theta, that's our b, and we have to try to find some kind of a, because this will give us a new upper bound for our integral. So how do we do that? Well, to find this a over here, we have to ensure that a is less than or equal to b. So if we take a look at just the sine of theta, we can ignore this r actually because it's always going to be that same constant r. It's not going to change. If we take a look at the graph of sine of theta, well, this is what it looks like on the interval 0 to pi. So we have the 0 over here, and we have pi over here. And what is a? Well, a is some function that's always less than or equal to b. So this sine function that we have over here, we can think of it as b. And we want to try to find some a that's less than or equal to b on the interval 0 to pi. Now, I guess before we do that, we need to make a couple of modifications to this integral because it is tricky to find that a function, because you could say, well, it's just 0, but that wouldn't be very helpful. What you could do is notice that sine is symmetrical across the point or the value pi over 2. So what you could do instead of integrating from 0 to pi on 2 and then from pi on 2 to pi, what you could do is half this interval. So instead integrate to pi on 2 and then just double the result. So you're just using symmetry of sine, you can do this. So now we just look on the interval 0 to pi on 2. We need to find some kind of a that's less than or equal to b. And as you can see, if we construct a straight line over here that connects the origin to this turning point, or this maximum, then we find a new function that's less than or equal to sine of theta on the interval 0 to pi on 2. And if we plug it into the decaying exponential, we in fact find a new upper bound, which is quite nice. So the final question is, what is the equation of the slide? Well, that's pretty easy to see. Notice that this is the coordinates pi on 2, comma 1. So if you do rise over run, well, rise is 1, run is pi on 2. Rise over run will just give you 2 over pi. And to construct the equation of the straight line, well, it's just y is equal to 2 over pi times x. So this is really quite nice. So we can plug this in because we found our a. This is our a over here, a function that's less than or equal to sine of theta. So if we plug this in, this is going to be less than or equal to 2 over r, integral from 0 to pi over 2, of e to the minus r. Now instead of sine, well, we found a new upper bound, we're going to replace it with 2 over pi times x. So 2 over pi times x, like so, and we integrate with respect to theta. In fact, this should have been theta because technically this is the theta axis, this is the y-axis if you want, so this should have been theta. Alright, so we found a new upper bound, and look at this. This function is a lot easier to integrate. That's exactly what we're going to do now. So this is now equal to, what do we have? We have a 2 over r, integral from 0 to pi over 2, e to the minus 2r over pi, times theta d theta. Integrating this is very easy. So what's the antiderivative? Well, we still have this exponential function, e to the minus 2r over pi times theta. But now we also have to divide by the derivative of this argument because it's linear. So what's the derivative? Well, it's just minus 2r over pi. If we divide by that, well, that's the same as multiplying by pi with a negative over 2r. Okay, so this is what we have now. Let's see what this evaluates to. And also we have to remember our bound, so that's from 0 to pi on 2. And this is now equal to minus 2 pi over, well, first of all, these 2's cancel out, so I guess we can just ignore that. So we have minus pi over r squared. And we have, if we plug pi into here, then we're going to get some cancellations. We're actually going to be left with e to the minus r. So we have e to the minus r minus the lower bound, but if we plug the lower bound into here, then we're going to get e to the 0, which is 1. This is minus 1, like so. And what happens now? Well, we just found a new upper bound. So this is this is an upper bound for our original integral. So let's plug that in. So now this integral over gamma, is less than or equal to minus pi over r squared e to the minus r minus 1. Aha. And now this is really good because we can take the limit on both sides. So limit as r approaches infinity on the absolute value of the integral over gamma is less than or equal to the limit as r approaches infinity of minus pi over r squared e to the minus r minus 1. And this obviously goes to 0 because we have r squared down here. E to the minus r as r goes to infinity, that's going to go to 0 as well. So this factor doesn't really matter. This factor over here, 1 over r squared, is ultimately what pulls it down to 0, which is quite nice. So in the limit, as r approaches infinity on the absolute value of the integral over gamma, since this guy is positive, it's in absolute values, the only way for this to be, the only way for this integral to be positive and less than or equal to 0 is if it's 0 itself. So yeah, that took quite a bit longer than I expected. Not sure if that's the most optimal way to find an upper bound for integral over gamma, but yeah, that's what I could think of on the spot. So we showed that the integral over gamma contributes nothing to our contour. Last thing we need to do is evaluate the integral over little gamma. So that should be fun because we're actually going to get some kind of value at the end. So let's take a look at the integral over gamma of f of z dz. Now again, just like with the integral over big gamma, we need to find a parameterization. So notice on gamma, every single z can be written in the form epsilon e to the I theta, which means dz is equal to I epsilon e to the I theta d theta. And now notice that theta, we're going to start over here and we're going to swing around over to here. What's the angle over on this side? It's pi, and we're going to go down to 0. So I'm going to use this funny notation, this funny interval notation that takes us from pi and it runs all the way down to 0. So this integral, I don't believe, no, we don't need to put bounds in this because we don't want to show that it equals to 0. That would be pretty silly because we have 0 is equal to integral plus 0 or something like that. So this is now equal to the integral from pi to 0 of f of z. But what exactly is f of z? It's 1 minus e to the I. Now z is going to be epsilon e to the I theta. This is divided through by z squared, but what is z squared? It's epsilon e to the I theta, but the whole thing squared. Is now our dz at the very end, that turns into I epsilon e to the I theta d theta. And notice the nice thing is over here we have this factor of epsilon e to the I theta. That's going to cancel out with one of these factors down here. So this is going to be equal to the integral. Let's actually flip the bounds a little bit because we want it to go from 0 to pi. And we have now 1 minus e to the I epsilon e to the I theta divided by, this is gone over here because we cancel, and we're just left with down here epsilon e to the I theta. d theta. And of course we can bring this I out to the front as well. So we have minus I integral. Now usually what I would do in this case is I would just take the limit as epsilon approaches 0, just pretend that you can interchange the limit with the integral and get some kind of result over here. That's something you can do with the integral of sine of x over x. If you check out one of my videos, the integral over this little circle, you can just bring the limit into the integrand and figure it out from there. But here it looks a little bit funny because we still have this epsilon on the denominator. So what we want to try to do is try to cancel it out with something up here. Now, in order to be able to cancel out epsilon e to the I theta with something up at the numerator, we need basically epsilon e to the I theta in the numerator, and the only way to get that is by expanding out e to the, well, the exponential function in its Taylor series. So maybe we'll try that. This is going to be equal to now minus I integral from 0 to pi of, let's see, we have a 1 minus, and now what is the Taylor series of e to the something? Well, it's the sum. Let's choose an index k going from 0 all the way up until infinity. Now the Taylor series expansion for e to the x is x to the n over n factorial, but now x in this case is this whole entire thing up here, so that's going to be I epsilon e to the I theta, and we raise all of this to the nth power. This is acting as our x, and we divide this through by n factorial, and all of this is divided through by epsilon e to the I theta. So maybe if I want to make this a bit more clear, we can isolate this over here and just take I to the n over here. So I to the n and then this guy to the nth power. That way maybe we can start cancelling things once we expand it out. And of course we have d theta here. Alright, so I want you to notice one thing, because I'm pretty sure, since we have a negative over here, if k is equal to 0, this should have been k. I don't know why I chose n, but k factorial down here. If we have k is equal to 0, then the first term of this Taylor polynomial should in fact be just, well, 1. Because k equals 0, that's going to make this whole entire thing 1, and then 0 factorial is 1. So the first term is going to be 1. What does this mean over here? Well, if we, let's actually bring this negative back into the integral. We're doing a lot of weird stuff over here, but this is now going to be equal to I integral from 0 to pi. If we bring this negative back in, that's just to make things a little bit easier to see maybe. So we have 1, no, not 1. Since we bring the negative in, we're going to switch these two around. So we're going to get the sum. Well, actually, I'll write 1 over epsilon e to the I theta first. Then we have the sum from k is equal to 0 to infinity of I to the k epsilon e to the I theta to the kth power over k factorial, and then minus 1. So we bring the negative in, we're going to switch those two terms around. And this is really nice because the first term of this polynomial, or this power series, is exactly 1. But we have a minus 1 over here, which means we can just ignore the first term. So we're going to subtract 1 off, and in fact we're going to start at k is equal to 1. Now when k is equal to 1, we're going to get actually positive powers of k over here on our epsilon e to the I theta. This is really nice because we can cancel over here with one of the factors here. So if we want, we can rewrite this as, how much space do I have? We have plenty of space. So this is equal to I integral from 0 to pi of, let's see, we have the sum running from k is equal to 1 to infinity, I to the k, and then epsilon e to the I theta to the k minus 1 divided by k factorial. Okay, this is good because now notice when k is equal to 1, then in fact the first term of this series expansion doesn't include epsilon, because if you plug 1 into this k, then you're going to get 0, but anything to the 0 is exactly 1. So this is quite nice. So what does this mean over here? This means that if we take the limit as our epsilon approaches 0, well, it's going to kill off all the terms of our polynomials except for the very first one when k is equal to 1. So if you imagine expanding this out, if we have k is equal to 2, 3, 4, and so on, there's going to be epsilons inside of our terms, or multiplied inside of our terms, and when epsilon approaches 0, those terms are going to disappear, except for when k is equal to 1, because when that happens, we're going to get a 0 in the exponent, and anything to the 0 is just 1, so there's not going to be any epsilons. So in fact, I believe what this should become is I integral from 0 to pi, and we have just left I to the 1 over 1 factorial, and then all the other terms over here are going to become 0 as epsilon approaches 0. And then we have a d theta. So this reduced quite nicely. So overall, what do we have? We have I times I, which is minus 1, 1 factorial, which is 1. So this is a minus the integral from 0 to pi, d theta. And well, this is just pi. So we have minus pi in the very end. Okay, so this is quite nice. We found that the integral over little gamma in the limit as our epsilon approaches 0 evaluates to minus pi. So let's add that in over here. This becomes minus pi. Very nice. And I think we should be done. We've evaluated all of our integrals, and now it's time to put everything back together. So what do we have? We have 0 is equal to integral minus pi plus 0 over here, but that doesn't really matter. Let's just focus on this bit of the equation. Let's bring pi onto the other side. And what do we have? We have that the integral from minus infinity to infinity of 1 minus e to the ix divided by x squared dx is going to be equal to pi. And now notice, I think I mentioned this at the very start, the reason why we choose e to the ix, it's easier to work with, but then at the very end we can take the real part and this will produce a cosine. Now why exactly is that? Well, we can rewrite this integral, let's look down here, we can rewrite this as the integral from minus infinity to infinity of 1 minus, now let's expand out this e to the ix because we have cosine of x first of all, over x squared, and then we also have a minus I times the sine of x over x squared dx. So that's what happens when you expand that out. I believe that's what you should get. And yeah, you can use a linearity of the integral to split this up and so on. And yeah, let's actually do that because this is now equal to the integral from minus infinity to infinity of 1 minus the cosine of x over x squared dx, and we have minus I times the integral from minus infinity to infinity of the sine of x over x squared. I'm not actually sure if this integral over here even exists. But regardless, that's the imaginary part. We don't really care about the imaginary part. We only care about the real part. So what does this mean over here? If we take the real parts on this side, that should be exactly the real part on the right hand side. But notice the real part of pi is just pi, and we just found that the real part of this integral is what the integral we started off with. So from here we can conclude that the integral from minus infinity to infinity of 1 minus the cosine of x over x squared dx is going to evaluate to exactly pi. That's the real part of pi, just pi. Pi is an imaginary. So I believe this should be the answer. So yeah, that was a very interesting integral. Probably the integral over little gamma was my favorite using that Taylor series expansion. That was quite interesting. But yeah, that's pretty much all for this video. I hope you guys enjoyed it. Guess this is going up on YouTube because I actually managed to get through it without any notes or anything like that. So yeah, once again, hope you guys enjoyed. Have a wonderful day, and until next time, yep, I'll see everyone later. Bye bye.